Thank you very much. And thank you for having me along. I'm just going to turn this one on to HDMI as well. So hopefully you've got two screens. Yep, there we go. That's great. So yeah, please don't hold the AWE thing against me. I work with AWE to do with safety and security. So I'm helping to protect you guys from people that would do naughty things with nuclear materials most of the time, and to make sure that our deterrent is kept safely and doesn't do anything unexpected. I also work with Sellafield on some of their thornier problems as well, which is a place up in Cumbria where we store the majority of our nuclear waste, and that's pertinent to some of this sort of story today. So I'm talking about diamond energy, and you'll understand what I mean by that as we go through. And really just to try and, I hope, to get you to think about nuclear in a different way in terms of the proposition. I should say that I'm obviously an advocate of nuclear energy. I'm also an advocate of low carbon energy, so all the forms of renewables, and see them as being very complementary to each other. And I actually would prefer to see nuclear in a different form of energy than it currently is. I think there are better technologies that we can utilise for nuclear, and I think we also need to think about nuclear energy and the proposition that we pose to government and to the public in terms of the least valuable thing we do or can do with a nuclear reactor is create electricity, actually. And that's the one thing that we've been doing with nuclear reactors since the 1950s, is just generate electricity. But there's much more value in nuclear energy than just electricity alone. One of the things you can get, Tim, is hydrogen, of course. We'll cover that. But of course, diamonds are best known for being the girl's best friend. And when I told my wife I was doing lots of research on diamonds, she got totally the wrong idea. She thought, you know, on a professor or his salary, you could buy a diamond like this. She was sadly disappointed on lots of different counts. But of course, diamonds are recognised internationally as being a thing of great expense, you know. You're going to shell out thousands of pounds for your diamond engagement ring. It's actually one of the biggest missold things in the world, actually. It's a real racket on behalf of De Beers, because actually in my labs at University of Bristol, we can grow diamonds for pence or pounds, which would be better than the diamonds they dig out of the ground and sell for tens or hundreds of thousands. It's actually very easy to make a diamond. What's quite difficult is managing to fool the whole world that these things are valuable, actually. But we'll get back to diamond in a second, because really I'm here to talk about nuclear energy. And this is a lump of uranium ore sitting in a cloud chamber. And that cloud chamber allows us to see that that material is constantly emitting energetic particles. It's giving off radiation. So for this lump of uranium ore, it would be a mixture of alpha particles, beta particles, and gamma rays. And usually, if you don't have a cloud chamber, you can't see that things are radioactive. In fact, this room's radioactive, I'm radioactive, you're radioactive, maybe I'm more radioactive than you are, but we're all radioactive, all things are radioactive. And of course, the sun itself is giving off lots and lots of radiation. And if we didn't have an atmosphere, then probably we'd all be dead, not only because of the vacuum, but because of the radiation levels would be much, much higher. So radiation, first of all, is all around us constantly. In a nuclear reactor, the intensity of the radiation is much, much higher. In nuclear waste, the intensity of the radiation given off is much, much higher than background levels. But there is no such thing as no radiation. That's very important to consider. So with that in mind, and talking about the fact that the value you could get from nuclear could be more than just electricity on the grid, I want to form the proposition that actually with some of our nuclear waste we could do, rather than just sticking it in the ground at the cost of many tens of billions, okay, we could do something else with it. We could actually recycle it, we could reuse it, we can be sustainable. Yeah, and I think that's the whole point of this lecture series, is about sustainable energy and resources. So with that in mind, we came up with the idea of the diamond nuclear battery. And we posted this concept a couple of years ago now, and we actually posted this video, and I'll play it in a second, but this video attracted something like 12 million views in less than 2 weeks worldwide, because I think people quite like the concept. So let's see if it plays now, because it played when we were practicing earlier.
Since the 1940s, the UK has run many nuclear reactors for research, military purposes, and electricity generation. These reactors all use uranium as fuel, housed inside of a core made out of graphite.
Let's just try that again, because it's supposed to play an animation and not just play someone's voice. But let's see. It's always what happens when you load it up and it works fine, and you do it again and it doesn't work. It's not even doing it now. Right, let's skip over that. It's a lovely music. It's a lovely voice. A guy called Dave that works for me. It sets a proposition, but I'll cover it anyway. So I've kind of said, is grid electricity the only thing we could get from nuclear power? And actually the answer is no. Because really when we're using a nuclear power station, we're converting the thermal component given off by burning the nuclear fuel, and we're turning water into steam, and we're driving a turbine, and through that mechanism we're generating electricity. But we're actually ignoring the other types of radiation given off by that nuclear reactor core. We're ignoring the gamma flux, principally, that's coming off, which is incredibly intense. And actually what we're doing is we're creating really thick shields of concrete and other materials to block the gamma rays getting out of the core. Now, that's good because it keeps people safe. But of course, when you take the spent nuclear fuel out of the reactor core, it's incredibly radioactive. And you then process that nuclear waste, and you essentially take out the nasty radioactive materials in concentrated nitric acid, and you double distill it into something which, if you filled up this bottle with highly active liquid effluent, then that's more radioactivity than released by Chernobyl. And Sellafield has thousands of litres of this stuff. So there's an awful lot of radioactive energy sitting in Cumbria and sitting in reactor cores. And actually, with the UK, we were quite unique in the fact that we had a specific type of nuclear reactor, and we've had 2 fleets, which nobody else really has. And those were the graphite-moderated nuclear reactors. So we were using graphite as a core material, which is stable up to very high temperatures, and we were using that graphite to slow the neutrons that come off the nuclear fuel, so that the chance of forming more fissions and keeping a sustained critical reaction would be possible. And most other nuclear reactors use water as the moderator, and they use that as a moderator and a coolant. But in our reactors, first of all, it's called the Magnox fleet, which was essentially modelled on the Calder Hall reactors. And then from that, the AGR reactors, which EDF now own and run, they all use graphite blocks with big holes down the middle where they could put the control rods and the fuel rods. And those reactors aren't cooled by water, because that wouldn't go too well with very hot graphite, but they're cooled by carbon dioxide. So it's a closed loop system, so it's not venting carbon dioxide. But as a function of time, that graphite has become activated. Okay, and if anyone's studied nuclear history, a great example of the energy that can be built up into nuclear graphite during operation is the wind-scale piles and the wind-scale fire, which was Wigner energy, which was built up through running of the air-cooled reactor, which then sparked a fire, which set fire to the metallic uranium fuel, and we had a nuclear fire and incident on our hands, which, if that happened today, that would have been regarded as big and as higher level as Fukushima, which would have been very unfortunate, but thankfully it didn't happen then. So in the UK, we have a legacy where we have about 90,000 tons of irradiated graphite. Well, that's about 2/3 of the entire world supply of irradiated graphite, and it's all ours, okay? And at the moment, it's destined to go into a deep geological disposal facility. So a kilometre underground, sitting there for the rest of human existence, pretty much. And all of that radioactive energy that's locked inside is going to gradually seep away and be intercepted by the rock surrounding it. So I think this is an opportunity rather than looking at this stuff as waste. Okay? And I'll try and explain why. The reason why is that carbon-14 is an isotope of carbon, which is a radioisotope. So it's a radioactive isotope. It has a half-life of about 5,000 years. So if you start with a kilogram of carbon-14, after 5,000 years, you've got half a kilogram. So it's a relatively long half-life relative to human timescales. But the important thing about it is it's formed in the upper atmosphere from interactions with solar particles, but it's also formed in nuclear reactors when you irradiate normal carbon. Okay? And normal carbon actually is 99% carbon-12 and 1% carbon-13. So for the 90,000 tons of nuclear graphite that have been in reactors, that 1% of carbon-13 is turned into carbon-14 through its exposure to the neutrons in the core. And so we've nicely converted that material and made it radioactive. So the current plan with this 90,000 tons is, first of all, it's going to stay in what they call care and maintenance. But it will stay in its host reactor core for 100 years. And that allows actually the radioactive outside of the reactor core, or the activated steel, to lose its radioactivity. But at the end of that 100 years, more or less what you have left with is carbon-14 being the major contributor to dose in this graphite. As a radioisotope, carbon-14 is a beta emitter. So when it undergoes radioactive decay, it fires out a really high energy electron. And that energy is sort of got a maximum energy of 156 kiloelectron volts, but typically an average or a mean about 49 keV. So it's reasonably high energy when you compare it to something like tritium, which is quite a weak beta emitter. So this is one of the biggest problems, you could say, by volume and by mass, in terms of this 90,000 tons at the moment has to go into a 90,000 ton hole in the ground, a kilometre deep. But what if we actually used it for something different? What if we actually used it for something where it became very, very valuable instead? I should also point out that nitrogen, which is a contaminant, a common contaminant of natural graphite, will also transmute to carbon-14 in a nuclear reactor environment. So not only do we get that 1% carbon-13, we've got some extra carbon-14 produced from nitrogen transmutation. So 90,000 tons and a half-life of 5,730 years. So that's about 900 tons of carbon-14 we currently have. So imagine if I could turn that 900 tons into something which wasn't waste. So first of all, that would save a lot of money from the UK taxpayer, because you don't have to pay for about a third of the geological disposal facility because you're just not using that space. But at the same time, imagine if you can make something that actually could sell for money. So you've got two sides to that business case, which is really quite nice. So of course, graphite, everyone recognises you use it in pencils for drawing because it's nice and soft and the sheets slide over each other very easily. Another form of graphite, though, is diamond, of course. And I have my obviously not real diamond that I can hold up at this point and say, the great thing about diamond is that it's got such amazing properties. And the key thing about the diamond structure itself, of course, is that in the diamond structure, you've got very strong covalent bonding between each carbon atom. It's so strong, in fact, that it means it's basically one of the hardest materials that we know. It also has fantastic thermal conductivity at the same time, and we would recognize it in materials community as a wide bandgap semiconductor, and that's really very important. So diamond itself, of course, we recognize as De Beers selling it with this idea that a diamond is forever, diamond batteries forever as well. But actually, for me, I really like the fact that it's so strongly bonded, because that means it's incredibly radiation hard. So if I stick a diamond in a nuclear reactor, it doesn't break, it doesn't degrade. If you stick almost any other semiconductor material into a nuclear reactor, you quickly break it. It quickly stops working. A great example of that is when they've stuck robots into the core of the Fukushima reactors. The cameras, which use semiconductors, last for about 2 or 3 minutes before the radiation kills them. And equally, radiation detectors they put in there, semiconductor radiation detectors, they are physically killed and they saturate immediately. Whereas diamond doesn't damage, doesn't break. And that's really useful because actually we can use this not only as an energy generating material, but we can use it as a detector material as well. And that will be part of my story. So for the idea of a diamond battery was to actually take carbon-14 from nuclear reactors, which are essentially turned off and sitting in a state of dormancy, and to recycle it, turning it from graphite into diamond. And in doing so, make the world's first radioactive diamond, or deliberately radioactive diamond, I should say. And really that came out of a number of different crossing areas of research. And I think you'd all recognise that the best types of research projects come when you've got lots of overlapping ideas. And this came, first of all, we were doing some really nice work on thermionics, so concentrated solar conversion, using diamond as the material that was converting that heat into electricity. And we've still got a program going on that. At the same time, we were working a lot with Magnox, and we also worked with EDF, looking at graphite and the distribution of carbon-14 in these reactor cores at the end of their life, to try and understand the distribution and also to work out ways of maybe extracting it at the same time. And I've had a number of PhD students who have successfully passed through the system on this, exactly this kind of topic. And then also working on detectors which can detect radiation at something like 24,000 times lethal doses. So the kinds of places where you need monitoring, but it's almost impossible to do it. And that was specifically, I'll talk about that, Sellafield is a great example. And also doing research into oil and gas at the same time, because diamond, because of its thermal conductivity and hardness, is a brilliant coating to put on cutting materials. And that will become clear why that's interesting later on. And also, I've put talking with shady organisations. It was actually BAE Systems, not AWE, who actually came to us to say, we think you could make some sort of nuclear power cell based on liquefied radioactive krypton that you could use to power a small submarine silently. And we said, whoa, we could. And the idea was that you could have a hollow diamond sphere filled with liquefied, pressurized radioactive krypton. And in theory, you could do it. But then we calculated how much radioactive krypton is produced by all of the nuclear reactors in the world annually. And that would equate to about 1.5 fuel cells that you could make. So nigh on impossible. But it got us thinking of the idea of diamond battery instead. And of course, if you do it right, you have this brilliant dual-sided business case for why you should do this. So one side is you're turning waste into something valuable, and maybe you're getting paid by the Nuclear Decommissioning Authority to process this graphite waste, and in doing so you reduce its residual radioactivity and it crosses the threshold from being intermediate level waste to low level waste. And that takes you from something like 46,000 pounds per cubic metre to 3,000 pounds per cubic metre, just crossing that threshold. And harvesting the carbon-14, we can then create small electronic power devices which would literally last thousands of years and make something valuable that people would want to buy. And I'm going to delve into some of the business case behind this as we get to the end of the talk. So back to basics. So I talked about diamond detectors and Sellafield. So this was actually the first glimpse of one of our technologies that we've been developing, in fact. So we've developed a detector that we call the Diamond Detector, which is now routinely used at Sellafield. And Sellafield is the site which has all of this radioactive material, and it has facilities where there are literally thousands of litres of highly active effluents, which, you know, one single drop escaping confinement would mean the site would have to be evacuated immediately. This is how dangerous this stuff is. And they need to be able to send in a device to monitor contamination of bits of plant and where the material is, because it's been, in some instances, it's been in very big storage tanks for about 25 years. And they don't know if the material is actually going to eat its way through the tank walls and escape into the cell that confines it. So the diamond detector works very simply. It's what we might call a leakage current detector. So we have electrodes on opposing faces of the diamond. This is a single crystal, typically about 4 by 4 millimeters by 0.5 millimeter thick. I'll show you a picture of one in a minute. And we put it into a very high gamma flux, and we put a 300 volt bias across. And what happens is the diamond detector generates a current which is proportional to the dose that it's receiving. It's a very, very simple device. And what that means is when you expose your diamond to a high flux of radiation, you get a current which is proportional to the dose which it's receiving. And the great thing about it is it's about the size of my thumb. It can go on a 150-meter armoured cable, so you can feed it in through the pipework into a facility. It's diamond, so it basically doesn't corrode. And you use noble metals as well, so they don't corrode either. Very simple to operate because it's operated by big, hairy, gorilla-type men at Sellafield's site without breaking it. Our first prototypes on site got broken all the time, actually. And it gives you real-time dose rate data, which is the first time they've ever had a technology which can do that, which means you can get dose as a function of time and position, which means that they can actually characterize their facilities in a way they could never before. Great example, but I've had to redact the unit so that I could show you, this is an example of diamond detector deployed into a nuclear cell. And the peak dose would be maybe on the order of something like 1,000 sieverts an hour, so about 500 times lethal, 500 times above lethal. And we lower the diamond detector in through the concrete shield. So the concrete shield is about 1.5 meters thick. And this is going in through the roof of the facility. And we start to lower the sensor down. Now, when we get to this red area, it's actually we're sitting between two tanks filled with this liquid effluent. And we're able to give a defined dose. And actually, because of some collimation we put on the device, it tells us roughly how full the tanks are filled, which is something that they just simply didn't know. Now, you can see we get some drops here. This is where the pipe that we've delivered it down has actually got double skin because they screw into each other. So the pipe thickness increases and it stops some of the gamma getting to the detector. But this is the type of data that they're recording now on a regular basis at Sellafield. And it works very, very well. So we pat ourselves on the back for developing a new type of technology which works from a low dose of about 0.05 grays per hour up to 24,000 grays per hour. And 24,000 is an incredibly high and extremely lethal dose. So one day we were playing in the lab with our diamond detector and a very strong americium source, and one of my postdocs forgot to turn the 300-volt bias on. And what we found is it still generated a current. Quite a small current compared to what you'd get for 24,000 grays, but it was noticeably quite high above background, just sitting next to quite a good lab source, but with no bias. And usually we would use the bias to encourage the electron hole pairs which form from gamma interactions to drift to the electrodes to actually produce that current. But it was actually acting on its own. It was acting essentially as a Schottky device, but actually without deliberately being configured as a Schottky device, because essentially this device was having two ohmic contacts. So essentially the ohmic contacts were allowing electrons to flow freely out of the device with no barrier. But actually it wasn't working like that at all. We were seeing a directionality to the current flow, essentially. And actually this was the first example that we know of a gamma voltaic. Of course, everyone's very familiar with a photovoltaic. And actually, we'd created the first device which was inadvertently doing exactly the same thing, but for a different part of the electromagnetic spectrum. And our program on this continues today, because with a gamma voltaic in a highly radioactive environment, you have the opportunity then to power sensors indefinitely. They don't have to have a chemical battery anymore. They don't have a battery, they just have a gamma voltaic on the outside. So great for nuclear waste stores and facilities where you might want to measure temperature, humidity, radiation level. You could even, with the idea that with some of these really highly active waste canisters, you could create a diamond shroud which sits around the outside and turns it from being just a waste canister essentially into a battery or a power pack. And you could start to power initially mission critical parts of the facility, so bits of monitoring to start with. Then you could think about powering fans, so you've got air circulation. But ultimately, you could deploy this technology in either generation 4 fission reactors or a fusion reactor, so you get direct nuclear electric conversion. So you cut out the thermal bit, and actually, potentially, this is far more efficient because current sort of EDF technology in the AGRs is about 35% efficiency in terms of converting the heat into electricity. Whereas this is far more efficient if it's perfected. And of course, diamond, because it's such an excellent thermal conductor, is very, very happy in hot places and doesn't degrade at all. So the gamma voltaic device is pretty simple. We have an ohmic contact on one side, which is typically nichrome, and then we have a Schottky contact on the other side, which at the moment our favoured one is aluminium, and then we have gold on the outside of that. So essentially we're making a sandwich, diamond sandwich, very, very simple. And we're using electronic grade undoped diamond at the moment, but we'll be increasing our boron dopings to improve the device. And you can just see there's an X-ray, a radiograph there of the diamond gamma voltaic. We're looking at it sideways on. So this is actually a 4x4 millimeter crystal, 0.5 millimeter thick. And you can see you've got the electrode on one side and the electrode on the back face. And you basically point that at the radiation source and it starts to generate electricity. Now, one of the ways we practice and test is with our lab XRT X-ray tomography system, which has got quite a powerful X-ray generator. And we stick our gamma voltaic right in front of the X-ray generator. And what we do is we turn it on, and as we wind in the X-ray source so that it goes very, very close. If you just look in the top right-hand corner, you can see the X-ray source being wound really close in. And you can see at the bottom here, this is the voltage that's being generated. Now we're getting up to 220, 240. The voltage that we would require, and we were talking power electronics earlier, to power a very basic sensor pack is about 0.1 of a volt. So we're really easily overachieving that in a not particularly high radiation flux, actually. And you can see once the source has finished being wound in, we go into lovely steady state production of current, and then if we wind it out, it goes back down again. This is a 4x4 by ½ mil thick diamond. It's tiny, but it's incredibly efficient. It's really very exciting. So this gives us our first diamond energy technology. We can look at harvesting gamma energy and producing electricity in very meaningful ways. So that was the first technology, that's gamma voltaic. But you can only use gamma voltaic in a high nuclear radiation environment, okay, places that would be lethal for us most of the time. And that's I'd say that's incredibly niche, actually, because you can only use that on nuclear sites. So actually, a better aspect of the technology is, well, what about if we don't take the radiation from the outside, but we actually lock the radiation on the inside? And we form something called a beta voltaic. And we call it a beta voltaic because we use beta emitting radioisotopes to provide the energy to drive the voltaic. So I talked about a sandwich before. This is a different flavor of sandwich. It's a sandwich where it's a continuous diamond structure, but it's isotopically layered. And in the center of that diamond is we have a layer of radioactive carbon-14 containing diamond. And with every beta particle that's emitted, if you design it right, that 50 keV beta particle is converted into a shower of electrons. And the great thing about diamond is it doesn't damage because it's so strong. And actually, the beta particle conversion efficiency in theory is about 95% efficient. So it's incredibly efficient. Now, there are other types of beta voltaic available, but they all work on the principle that you have an emitting material and a collecting material, and there is always a gap or a discontinuity where they come together because there's a material mismatch. You get absolutely huge energy losses across the gap, so the efficiencies are incredibly low. And what we've done in beta voltaic technology is throw away the gap, throw away the discontinuity. It's just a single structure, and therefore we can't get those losses because it's not possible. There's no interface. So there are actually three ways you can make a diamond power cell beta voltaic. The first way is controlled processing of the graphite to release a gas, and you turn that gas into methane. And from that methane, you mix it with hydrogen. This is why we'll be talking later, Tim. And you grow the diamond by a process called chemical vapor deposition. But essentially, you spark a plasma. Typically, we either use very hot filaments or we use a microwave. And in that hydrogen plasma, it causes the methane to break up and for the diamond to be deposited down on a substrate surface. Now, the quickest way to grow diamond is to grow directly on a diamond, but you can grow on other materials. Typically use things like tungsten or iridium. If you have an iridium single crystal, you will grow a diamond single crystal on top, in fact. And so we can grow a radioactive diamond layer very easily as long as we have a radioactive carrier gas. Now, of course, you can use a carbon-14 methane, but if you want to spice things up and increase the power output, you use a tritium plasma instead of a hydrogen plasma, and you incorporate tritium into the interstitial spaces in the diamond, and it's trapped there and can't get out, but it's beta emitting as well. So with this process, we process our graphite, we create essentially an isotopically labeled carbon-14, we grow the diamond, and then we would finish off the diamond device by putting on the metal layers on the outside, which is a technology we've already mastered, and we use that for the diamond detector. So a number of different steps, but one of the key steps is chemical vapor depositions, because this is a well-established process, and De Beers use it all the time. But this is the first time in history where actually people have wanted to grow isotopic diamond. It's the first ones ever, in fact. So normally you have your 2% methane and you have your hydrogen carrier gas. And if this was normal diamond growth, then you're about 1% effective in terms of converting the methane into diamond. Most of your gas goes straight out the back of the machine, up the chimney, and out into the environment. And of course, if you're using carbon-14 methane, well, I think you can imagine. You release a radioactive gas to the atmosphere in large quantities, okay? You're wasting your carbon-14. And of course, the Environment Agency then gets very cross, and I think the initial fine would be 2 million spot fine, and probably I lose my job as a professor at the University of Bristol and maybe even go to prison, who knows. So if you want to grow a radioactive diamond, you can't do it the way that everyone else does. You have to do it differently. And so part of the technology we've developed is something called closed loop CVD. So we close the loop so that we don't lose any gas material from the system. We essentially recycle it. And it is a very simple concept drawing because I can't show you exactly how we do it because we're patenting it at the moment. But essentially we're monitoring constantly the gas composition and making sure it's just right for diamond growth. And in doing so, whether you want to use carbon-14 methane on its own or you want to use tritium with it, you don't waste any material. You don't release anything out to the environment. And this is the technology we've been working on. We know it works. We haven't grown a carbon-14 diamond yet, partly because I haven't got all the safety cases in place. But we have grown the world's first ever isotopically pure carbon-13 diamond. And that's actually a diamond which is harder than diamond. You may be surprised to know. And that's because actually the atoms are just a little bit closer together. And because the atoms are a little bit closer together, it makes the diamond much harder. And that's potentially very, very useful for the oil and gas industry for digging holes. Because you've got something which is not only harder, but it's got a higher thermal conductivity than normal diamond, which is recognized as having basically the highest thermal conductivity you could have of any material. So on its own, that's quite revolutionary, I would say. There's a quicker way, though, because I have to wade through lots of safety paperwork to justify why I should be able to play with horribly radioactive gases in my laboratory. And Rich, who used to be at Bristol, knows that that can take time and causes lots of scars. There's a quicker route. The quicker route is I can grow a diamond via chemical vapor deposition. I can grow a carbon-13 diamond, and I can grow that in a deuterium plasma, so that I've got a diamond which contains deuterium and carbon-13. I can then take that diamond and I can put it in a nuclear reactor core. And essentially a bit like putting it in an oven, I leave it there to bake for a bit. And after about a month, I've nicely activated that diamond. I've converted a good proportion of the carbon-13 to carbon-14 and a good proportion of the deuterium to tritium. You then bring it back, grow a little bit more diamond on the outside, which is what we would call our gain or amplification layer. It's the layer which converts the beta particles into electricity. You put the metal contacts on the outside and there you go, you have your diamond battery. So the only problem is we don't have any nuclear test reactors in the UK. So I actually use a reactor in Japan, owned by the University of Kyoto, but it's based in Osaka. And this is one of the oldest test reactors in Japan, built in 1965. And actually, I've just finished my second lot of irradiations, which is 12 diamonds, which are currently on a ship or on a plane, I guess, coming back to the UK to be turned into diamond batteries. But we've already done one campaign already, and we've got another campaign going on in the summer. We get this for free because we've got a nice strategic partnership with them. If I was to have to pay for this, I'd have to pay millions of pounds, literally £1 million a month, to run a nuclear reactor and get this. And what that does is it activates not all of the carbon into carbon-14, but enough that we can create a low-power device, something which probably gives something like about 10 microwatts. And it's relatively small loading, so some of the nitrogen that you would have will convert, your carbon-13 will convert, and if you do put deuterium in, that will convert to tritium, so you have different isotopes. If you were to run in a test reactor which has fast neutrons, then you'll actually generate another beta-emitting isotope called beryllium-10, and that's a very powerful beta emitter. So depending on how flexible your test reactor is, you can grow in different radioisotopes. So you can have different flavors of diamond battery made this route. So it's really useful for prototyping, but it would never be the type of diamond battery which gives us our highest power output. The highest power outputs will always come from the high purity carbon-14 tritium type devices, which I've already told you about. And in the last year, we've developed a third route as well, which is you grow your entire device minus any carbon-14, but you grow a Schottky diamond device, all finished with its metal electrodes and everything, and you stick it into a system, the kind of system that you have, Tim, where you expose it to hydrogen at a relatively high pressure and temperature, and you infuse the diamond with deuterium, if you want to stick in a reactor for activation, or you infuse it with tritium, which is the quickest way. And conceptually, within the diamond structure, you can have a one-to-one ratio of hydrogen isotopes to carbon isotopes, because they fit in every interstitial space. And once it's in, it doesn't come out very easily unless you literally set fire to the diamond at over 1,000 degrees C. And so we're working closely with the AWE and with Culham, because they're the only two places which have tritium in the UK, to move towards very quickly producing some tritium-infused diamond batteries. Now, the disadvantage is the fact that it's tritium instead of carbon-14. So instead of lasting 5,700 years to get to half power, because the half-life is only 12 and a bit years, it means it gets to half power in 12 and a bit years. But you can pack a lot in. So you still get a lot of power, but for a relatively short period of time. To the point where, with a really high-spec device, you power a mobile phone for at least 12 years. Quite impressive. So tritium is potentially useful. It's also relatively plentiful. And we stick it in all the interstitial spaces. It's the easiest for us to make, provided we can measure the solubility experimentally of hydrogen in diamond for different pressure temperatures. And then we create a system where we can actually do infusion using tritium, which we know we can do, and we know where we can do it. We just need to calculate our solubilities experimentally first. So let's move on to market applications. So the key thing in terms of selling a beta voltaic device is that the amount of radioactivity inside is absolutely huge, to the point at which most safety advisors would look at it on paper and go, what? Didn't know we could have this much radioactivity in the university, okay? Because you're talking gigabecks to petabecks of radioactivity for a really big device. And that's actually the same issue that you have with beta lights, so tritium-based beta lights that you would maybe have in an emergency exit. Really high specific activity, but actually very, very harmless. And that's the bit that's really important, because if it's locked up in the diamond core, because the diamond's so dense, and if you design your device right, none of the radiation ever gets out because you're converting it into electricity. And you'd actually get less radioactivity off a diamond beta voltaic than you would off a banana. A banana, you get some dose from the potassium-40 that's in it. And so these devices will be intrinsically safe. No radiation on the outside, lots of radiation on the inside. And of course, if it's carbon-14, you hit half power in a very long time in the future. So how do we use these things? Well, the first thing is, lots of people have said, could you power a car with a diamond battery? Strictly no. The energy density is very, very high, but if it's carbon-14, it releases the energy very, very slowly. And so it trickles out. So it's a trickle current device. So the best way to use it is to couple it via a voltageless monitoring circuit with a very low leakage capacitor. So you slowly charge the capacitor, and when it gets full, the capacitor would discharge into a working circuit and power something like a sensor or a specific device. And we've been doing lots of work developing these types of sensory device which match the power electronics against the output capability of our devices, based on the fact that we'll be somewhere about initially 10 to 50 microwatts power, which is really quite small, but it's enough to power a device. So burst electronics is really what we call that. So if we think about the product features, the two detrimental things is initially it's going to be very expensive. Until we've got the Nuclear Decommissioning Authority paying for us to get rid of their graphite, we have to buy the radioisotopes, we have to pay for a nuclear reactor to irradiate them. And it does have this specific high activity which we need to get regulators to understand. But actually there's a precedent set for that in America. But of course you've got very long life, very robust because diamond's such a hard, strong material. It's got a low power but high energy density, very reliable because it just gives you a trickle of current permanently. So with a chemical battery, it will degrade over lots of charge-discharge cycles. Radiation damage would kill a chemical battery quite quickly. There's a very low EM signature, so those people who in GCHQ might be interested in sort of bugs and listening devices, apparently that's a good thing. Very low maintenance, chemically resistant because diamond won't dissolve easily in acids. And of course, they're designed for these applications where we can use sensors, we can put them in extremely harsh environments and just forget about them. You never have to go in to replace the battery because it never needs a replacement. And that opens up lots of opportunities. And biocompatible, diamond's biocompatible. It's been proven lots of times. So we can make use of that. So the most obvious route to go is coin cells because they're very cheap to manufacture. I mean, you can buy a full manufacturing capability and you can fit it in Tim's lab. It probably wouldn't cost you more than about £50,000 to do that. And this will be one of the first sort of applications where our batteries at about 10 or 50 microwatts output would be a brilliant replacement in things like watches, for example. But voltage, typically about 1.8 volts, although we will have special types which can go a bit higher than that. And the weight is actually very, very low because it's just carbon at the end of the day. Compare it to something like, for space applications, a plutonium fuel cell. Plutonium is basically the heaviest material we've ever played with on the surface of the planet. You can easily replace that with diamond for similar energy densities. In terms of the business case, if you solely focus on using carbon-14 methane and maybe with tritium as well, and you just grow the CVD manufacturing route, your battery cost for about 10 microwatts of about £34 for a battery. So that's a bit more expensive than the batteries you buy in the supermarket, but this one doesn't run out. So that's the big selling point of this. If you do this by the tritium infusion route only, so no carbon-14, it drops the price to about £3 for a power cell. Obviously, the lifetime's not there. And so most of the cost in terms of setting up this as a business proposition is the cost of the reactors for growing diamonds in literally batches of tens of thousands or millions. So ARM, who make the computer chips, sit on our advisory board. They said, if you had this technology available last year, we would have bought 2 billion. I can't make 2 billion yet. I can make about 12 at a time. So it's going to be a big, big investment to upscale this for commercial production, obviously. So we're still very much in our infancy. Markets I'd love to go to, because when we first launched this idea, we basically posted the idea of #Diamond Battery. Send us your ideas for this technology. And we had something about 10,000 replies. Lots of different ideas, from tracking elephants in the savannah to golf balls with locators inside of them. But lots of people came saying, could you do medical devices? Could you do pacemakers? Could you do hearing aids? Could you do implanted devices for monitoring blood sugar levels, for example? And actually, this is a really good market to go into because people are living longer, more people are having heart problems because more people are obese, more people are having diabetes as well. And so for a 10 microwatt device, this is perfectly suited for plugging into the pacemaker market, not taking over the market, but even a small slice is quite a lot, 7.5 billion for the market, and a really healthy growth rate year on year. You can use them as pacemakers. Of course, the earliest pacemakers were plutonium-based. Who would want that inside of them? But diamond could very easily replace that in terms of not only the power that's required, but in terms of the size. So it'd be about 6 cubic millimeters would be enough to power a pacemaker. It's really very small. The bigger one, the one that I really love to go to, $1.7 trillion is the Internet of Things market. You don't have to take over the whole market, but just a small slice of that would make me very happy. I could buy out the University of Bristol and tell the Vice-Chancellor what he should do or shouldn't do. But if you're up to about 50 microwatts output, then that enables lots of different things, lots of sensory applications that we're currently working on. Simple things like you can build devices, sensory devices, which for large civil structures like bridges or dams, you can put the sensors inside the structure as you pour the concrete. And using ultrasonic arrays, it can send health monitoring data out on a regular basis. So it might be once a day, once a week, once a month. But the point is that it will keep doing it. And it's much better for these large civil structures for you to monitor them from the inside than the outside, because it's more sensitive. So you've got applications like that. You've got applications anywhere where it's just difficult to go. So nuclear is going to be a first recipient of this technology, deploying these kind of devices in nuclear waste stores. But the applications are endless. I talked about golf balls, elephant trackers, lots of people wanting their cats tracked. But you've got applications in space and satellite technology. So long-distance spacecraft that would leave the solar system. Once you get to the edge of the solar system, there's not enough light coming from the sun to power photovoltaic. So how are you going to get it out? NASA have got a real problem in that the Russians won't sell them isotopic plutonium anymore for their power cells. So NASA don't have the capability of sending a long-distance spacecraft anywhere because they don't have a long-lived power cell to be able to power the electronics as it goes very, very far from the Earth. For automotive industry, this is a great one, tyre pressure sensors. You need 4 per vehicle. Brilliant. Really low power, but just monitoring when your tyre pressure is getting low, sending a signal to the car, comes up on your dashboard that you need to go and put some air in your tyres. Brilliant, absolutely brilliant. And you've got ecological, environmental things, including downhole monitoring for chemicals. Gas sensing is possible as well. And we should never forget the sporting goods. Some very serious South African investors wanting to create golf balls with diamond batteries inside. They were serious, we weren't so serious about that. So just to finish, because I've talked about diamond batteries, I've shown you a gamma voltaic working, I thought I'd finish the lecture by showing you all a nuclear power cell, beta-type nuclear power cell. This one's tritium powered. It's all nicely encased and coloured yellow, because that's what my safety people make me do. But yeah, this is a device which gives out about 3 volts. The actual current output's relatively very low, but this is one of the earliest devices. And so give them about 3.2 volts, which is reasonably healthy. About 0.6 microamps, so it's very small current, but actually it's not bad as a start. So if anyone wants to say they've held one of the first nuclear power beta batteries, please do pass that around. And thank you very much for your time, and thank you for listening.
Very kindly agreed to take questions and comments from colleagues.
Steve.
So one of the things that you mentioned early on was the fact that these electrons from this beta emitter won't get through the thing, because obviously one of the things that everyone's going to scare everyone is the idea that you've got some radioactive material in your pocket. So how much, what is the sort of penetration?
So, great question. So your tritium beta particle, which is relatively low energy, its maximum range is about 200 nanometers. So it's tiny. For a beta particle, it gets up to about a micron. But these devices essentially are very, I refer to them as being surface area devices, because they are so thin. So the kinds of thickness that we're talking about for the actual diamond, the actual thickness of the diamond is about 20 microns. And then you've got your metal terminations, and you'd repeat, just like the coin cell application. So you'd grow those layer on layer. So for us, iridium's quite an interesting metal. It's not the cheapest metal, but it allows us to potentially grow single crystal layer on layer. And we've done some really interesting work that we haven't published yet, which looks at the metals you can use to create Schottky and ohmic contacts, because what you want to do is swap contacts, so ohmic to Schottky, and you keep stacking that way. And actually what that research tells us is actually the metal's not that important. What's really important is the as Tim was saying, the interface, the terminating layer between the diamond and the metal. And it depends on what terminating atoms that you have. So if you terminate with hydrogen, then you tend to, almost any metal that you use as your coating, you'll create an ohmic contact. So that's great for one side. If you terminate with other elements on the other side, and I'm not going to tell you what ones, then you can very easily make a Schottky device with really quite a high barrier height. And that's the perfect sort of combination. But actually, it quickly steered us away from having to look at, really very expensive metals like platinum and palladium for one set of contacts, and told us actually what you just got to concentrate on is the terminations. And pragmatically, that's actually much easier once you've developed the methodologies.
Any other questions or comments?
Yes.
I was just going to ask about clearly you've been doing it in layers. Is there a kind of surface area volume ratio thing going on? I mean, is it better to look like a perfect diamond, or is it better with layers?
So it's actually I can split the answer. So if it's a beta voltaic, it's you have a very low aspect ratio, so about 20 micron diamond, then your metal, and then repeat and repeat. If you're a gamma voltaic, you actually want to be much thicker, because your interaction probability of any incident gamma, if your gamma's got very high energy, the probability of it interacting with your diamond is actually quite low. And all likelihood is the gamma just goes straight through the diamond and doesn't cause an interaction, just like it would go straight through you and me. If the energy of the gamma is lower, then the interaction probability is much higher. But of course, the thicker your diamond, the greater your interaction probability. Simple attenuation calculations would tell you that. So the thing about that is it's quite difficult to grow a very thick diamond. So 20 microns is really easy and really quick. If I want to grow 10 millimeter thick diamond, there are places that can now do it, and it's better than a natural diamond, and it costs you about 30, 40 quid. But there's only a few places that can do it, and they're very specialized, and they have very, very high power microwave growth systems. But Sumitomo in Japan, and then there's a company in Seattle that can grow them, and they're more or less just growing them for the gem industry. So they produce 30 a month, sugar cube sized, and they sell them to jewelers who then cut them and facet them, and they sell them on for many tens of thousands of pounds. Which is amazing. So yeah, so for a gamma voltaic, we want it to be thick. For a beta voltaic, we want it to be thin and lots of stacks. The interesting thing is if you put a beta voltaic in a gamma flux, it will also act as a gamma voltaic at the same time. So you can get an extra power boost by putting a beta voltaic into a nuclear environment.
Clearly what you've got at the moment is, well, one, very exciting, and two, very low current output.
Yep.
In terms of actually stacking that in parallel to increase your current capacity at the same voltage level, have you got any ideas yet? I realise it's early days, but have you got any ideas yet about what the sort of the physical aspects could be in terms of doing that stacking arrangement within a single enclosure?
Yeah, so we've got concept system designs actually, and in the next 12 months we're going to start to try and make a small pre-commercial production prototype. It involves the coupling of CVD and PVD, physical vapor deposition, using magnetron sputter guns in the same chamber, with some masks that you can pull in and out. If you're going to grow in a microwave plasma though, the shape of the chamber and being a uniform shape, a symmetrical shape is actually very important. So one of the other routes that you could potentially do it is, and this would be much better for large-scale production, but we're not sure if it's possible yet because of how brittle diamond can be, is to grow on essentially off a spool of wire. And you grow concentric layers, just like in a wire you'd have in your house, you've got concentric layers. We could grow concentrically like that, and then depending on what power output you want, you just cut it to the length. In concept, that's possible. And now that we know that the diamonds will be much thinner than we initially thought, it does lend itself to that concept. And in that route, you could use a hot filament CVD system. So you have an array of filaments sitting around your wire, and you pull the wire through the filaments, and you just have your plasma zones where the filaments are. And so you can be growing in one continuous roll from spool to spool. That's quite a long way off. That's very, very early concept.
In terms of the total energy generated from this entirely new and interesting source, percentage of the current global energy output, most of which remains carbon-based, although it's changing, can it replace or supplement?
Well, yeah.
How relevant is it to the greenhouse effect?
It's completely irrelevant.
Yeah.
So this is a technology which lends itself to very small power devices, but in places where you wouldn't want to go back for them. So one of the most fun examples is we've been developing these things called dragon eggs. So we use our low power electronics, and if we want to, we can put a diamond battery in, but at the moment we're not. We're using very small PVs. These are piezo triggered, so any vibration will trigger them, and then they'll start to measure various things: temperature, humidity, gas composition, position, and we'll send it using low RAR up to about 16 kilometers. We call them dragon eggs because we drop them on top of volcanoes, and we use them for volcano monitoring. So this is a volcano in Papua New Guinea. If you were a human being, where that drone is now, you'd instantly die from asphyxiation and a lung full of essentially sulfuric acid, and then the thing would erupt on you and you'd die. So we use drones to drop these things off and instill them right in the caldera of the active volcano to provide real-time monitoring with very low power consumption. And when the volcano blows up, we just send the drone out and it drops off another one.
Is that the size of a dustbin or this one?
No, it's about that size. Yeah, it's about that size. I'm glad you asked that question because I really wanted to show that.
Coming back to the long life of the carbon-14 system, you're saying that it's many thousands of years. Isn't that a sort of problem? Because if it's going to last that long, you only need to make a massive batch to start off, and then it'll keep you going forever.
Yes, well, it's so. For example, so NASA and the European Space Agency today emailed me and said we've submitted a grant for you. Never even heard of this guy. So we've submitted a grant for you on the diamond batteries for space applications. Could you please send us some information about how the technology actually works? I was kind of incensed but happy at the same time. For certain applications, carbon-14 is perfect. So geological disposal facility, large civil structures, space applications. But the route that we're really aggressively pursuing is the tritium-based beta battery. It's got much shorter half-life, so 12.5 years, but it has a much higher power output by comparison because the activity is much higher. And those kind of ones you could use for a pacemaker, and by, if you've got high enough power output, it lasts you 40 years, and then more or less it's done. So the tritium-based device is the one that commercially we're going to pursue first, and then the carbon-14 one, by comparison, will have a narrower appeal, I think. Also, it will take longer to develop.
If you build your battery out of carbon-14, complete carbon-14, it turns into nitrogen, I think.
Yeah.
So how long can you wait until the lattice breaks down?
Well, yeah, it would ultimately, yeah. So it will happily take up to about 20% nitrogen conversion. And so, that's a good couple of thousand years or so before you get anywhere near that. There may actually be some benefit as well to the nitrogen being bred in terms of accentuating the power output.
I know you said there's lots of applications where you wouldn't want to go back to the battery and it's basically becomes integrated.
Yeah.
If we look at those applications you were talking about where they're much more distributed throughout the economic system, and they haven't got a 5,000 year or half-life, but let's say we're talking about them becoming uneconomically viable after 50 years or whatever. What are the disposal issues that we face?
Well, if it's a tritium-based device, you only have to go through 5 half-lives before basically they stop being interested in it. So, 12.3 years for half-life, so 50 to 60 years is not a problem at all.
But you've got a lump of glass.
You've got a lump of diamond. That could be valuable in itself. It depends on whether it's a single crystal or a polycrystal as to whether it has any gem-type value. But of course, the diamond won't burn until you're getting on for 1,000 degrees C. So it's pretty robust. If you are going to use it in pacemakers, you'd use the tritium-based one. And if it did accidentally get put through an incinerator, the instant dilution you'd get into the atmosphere would mean it would be undetectable in terms of tritium level or carbon-14 level.